I'll just call you and
All right, gang, if I can have your attention. Sorry about that delay. So we have this. This is just, given a buffer solution, what is the pH of it? So there is a mixture of an acid and its conjugate base. There's two different ways that you can do this. They lead you to the same answer, though. One way, okay, so the first thing given in this question was a base, NH3. And then it's mixed with its conjugate acid, NH4 positive. You could say, all right, now by the way, never in a buffer does the acid react with its conjugate base. They'll always be on opposite sides of the equation. So you have NH3, a base, doing what bases do, accepting a hydrogen ion from water. And so it makes, when it takes a hydrogen ion, it makes the ammonium ion and hydroxide. Now because NH3 is a reactant, we use its Kb value. So you have the initial concentration of this reactant and this product. We could go through and do the equilibrium calculation, fill out the ice table, and find what the pH is. The other way to do it, we'll stick with this one, but I'll just show you how else we could do it. We could say, okay, well, you could certainly start with NH4 and treat it as an acid, and you don't even need the water in here. You can just say NH4 positive yields NH3 plus H plus. And that would be fine too. Now, because we're starting with NH4, which is an acid, we would need to use its Ka value. The Ka of NH4 and the Kb of NH3 are related to each other. They're not the same thing, but how are they related? They multiply together to give Kw, right? This is just that divided by, or into Kw. So anyway, it doesn't matter which way we do it. You could do it either way. You'll get the same pH value. So we'll just do it this way. And running through this, we have initial concentrations of both things. Now in chapter 14, we never had any concentration of the products. It was always just, okay, here's the reactant. Assume both of these are 0 and find what the pH is going to be. But now, because we're dealing with buffers, which is a mixture of an acid and its conjugate base, you'll have an initial concentration on both sides, like that. Now we assume that the hydroxide is 0, it's very close to 0, not exactly. So as this NH3 works as a base, it shifts to the right, and it goes down by some amount x, and that goes up by x, so does that. So in equilibrium we have 1 minus x, 1 plus x, and x. Kb is 1.8 times 10 to the negative fifth. And that's equal to x times 1 plus x over 1 minus x. And we've done enough of these. There's no big surprises anymore. The math always turns out to be so nice when you have the same amount of acid and conjugate base, or the other way around. The plus x and minus x terms cancel out, and we're just left with x. Now be careful, x is the hydroxide, not the hydrogen ion concentration. We started with the base. So x is the hydroxide, and that's equal to just 1.8 times 10 to the negative fifth. Because we have x times 1 over 1 equals 1.8 times 10 to the negative fifth. Yeah? So the pH, the pOH is going to be 4 point something, then subtract from 14, and I should know this just from memory. What is it? 9.26 or 25, something like that? Yeah. Actually, I think it was 9.255 when I did it, so that makes 9.26. But I mean, plus or minus a hundredth of a pH unit is fine. Anybody have any questions about that? Yes. A lot of the problems are going to have multiple parts. It'll say in the problem, you have this buffer, this acid and its conjugate base, or this base and its conjugate acid. Here's the pKa, or the Ka value. Number one, or part A, what is the pH of the buffer? And then part B, 0.5 moles of acid, strong acid are added to it. What's the new pH, that kind of thing. So, but you'll usually start with this, just finding the pH of the buffer before it's messed with. Yeah, this is very common. Okay. Now here's another example of, this is just like what I mentioned too. We have a buffer, it's a different buffer. Nitrous acid and the nitrite ion, acid and its conjugate base. Part one is going to be give the pH. On the next slide, part two is going to be 0.1 mole of NaOH is added. What's the new pH? First though, take a moment and see if you can come up with a chemical equation for what this buffer is going to be like in water. All right, here's what I'm hoping that you can come up with. Simple. Just like we did in the last chapter. It's acid dissociating in H plus and its conjugate base. Now we need the pH of it, so we need some concentrations. And the concentration is going to look like that. We have 2 molarity of the acid and 2 molarity of the conjugate base. We're given the Ka value. And there's another example where we find the concentrations are the same, so the math is going to be very simplified. Yes, the reaction is going to go to the right, and we're going to have a Ka value of x times 2 plus x over 2 minus x. And just like in the last problem, yeah, anytime you see an acid and its conjugate base with the same amounts, the hydrogen or hydroxide concentration is just going to be equal to the Ka or Kb. What do we get for a pH on this? Negative log of 4 times 10 to the negative fourth? 40. pH equals 3.40. So far, so good. Anybody have any questions about this? Now, 2 examples in a row, almost the exact same thing. Go ahead, Grace. First of all, the Na is a spectator. Don't put any of the non-reacting positive or negative things in. How do you know which one to write first in the reaction, right? I find it easiest to put the acid in the reactants because it's simpler to write the equation. Acid yields hydrogen ion plus whatever its conjugate base is. You could definitely have taken this thing and written NO2 negative plus what? NO2 is the base in this thing. This base is going to take a hydrogen off of the water and leave the water as the hydroxide ion. This would be fine. This would get you to the same pH. It's a little bit more work though, because you got to find X, which is the hydroxide ion, and then change it over to the hydrogen ion. I would just keep it with the acid on the left.
No, like what? That was.
Are you wondering if they react with each other?
Yeah. You know how there's HNO2 and NO2?
Yeah.
So those two like can be different. So like, which one do you put in the reactions? Like HNO2 or NO2?
You can put either one in. Just make sure that whichever one you put on the left, you put the other one on the other side of the equation. Don't react them with each other. Like you would not say HNO2 plus NaNO2. Or I'm going to leave the Na off. I don't want to see any spectators in these. Don't try to do that. They don't react with each other. Even though you say, oh, well, that's an acid and that's a base, well, how come the acid doesn't just give its hydrogen to the base? Well, what would you get if that happened? You'd get the same thing, right? So, yeah, you're going to have one of the buffer components on one side of the equation, the other buffer component on the other side. I'm not answering your question, though.
It's okay. Just pick one. And then you do it.
There's going to be one that's an acid. Put the acid on the left. It's going to be simpler than putting the base on the left. So that was part one. A buffer is given. What's its pH? Part two is like this. So you have 2 molarity of your buffer. 2 molarity of the acid, 2 molarity of its conjugate base are mixed together. Then we have this thing that I compared with the vicious dog attack on Friday. We have some strong base thrown in there. And the strong base is looking for some hydrogens to rip off of somebody. So we're going to have to do our 2 steps. One of the steps is the stoichiometry step that goes all the way to completion. And then once we have the after attack of the sodium hydroxide, then we, with the new concentrations of the acid and conjugate base, what is the new pH? Well, let's see. Hydroxide ions are dropped into this buffer. What buffer component is going to respond and neutralize it? The HNO2, right, the acid in there is going to respond to this attack by a strong base. So the reactants are going to be HNO2 is going to react with the hydroxide ion. That's what it looks like. Notice the arrow. It's not like, oh, they just mess around for a while, kind of play fighting, and then they become friends again with the arrow the other way. No, they go until the fight's over. One of them has to run up. Hang on. Got it. Thank you. Okay, so now for this step, when you do the stoichiometry, the unit has